Hello, everyone. Welcome you all to the part two of the introductory session of the analog laboratory. So now I'll present the screen. So this is Professor Deepika from Sai Vidya Institute of Technology, Department of Electrical and Electronics. So, in the last video, we were discussing about the cycle one experiment. That is only one experiment we have discussed. That is with respect to the rectifier circuit. That is how to rig up the circuit and how to do all those things. So that we have studied in the last video. So in this video we are going to like in this video we are going to study in this video we are going to study about how to build the logic gates, that is how to rig up the circuit by using the logic gates, and we will study one by one what are the different types of logic gates. So coming to this is actually the second experiment in the cycle one. So the logic gate is nothing but what? It is the logic gate is nothing but it is something like the combinational gate or combinational circuit, we can say. So these logic gates will be used to perform the Boolean functions, or it is used to perform the logical function. So these are nothing but these are called as the logic gates. So the gates which are used for the implementation of the Boolean function, or or to perform the logical function. So those are called as the logic gates, and these are very, very, very important in building any computer or any electronic circuits. So that means wherever the logical calculations are included, so that these gates plays a very important role. So next, coming to the what are the basic gates, universal gates, and the special gates. So the basic gates are nothing but what? These are usually the NOT gate, AND gate, OR gate, and the XOR gate. So these are usually the basic gates. And coming to the universal gate, so the universal gates are usually called as NAND and NOR gates. So by using these NAND and NOR gate, we can implement any type of function or any type of Boolean function, or we can implement any type of gate. That is nothing but what? By using NAND and NOR gate, we can implement all these basic gates. So therefore, these are nothing but the universal gate. By using only NAND and NOR gate, we can build any type of gate, so or any type of function. So therefore, these are called as universal gates. And coming to the special gates, so usually these are something like a combinational circuit, that is usually in the adder circuit, then in the subtractive circuit, multiplier circuit. So we'll be using the XOR gates, okay, XOR gates and the XNOR gates. So those are called as the very special gates, okay. So these are with respect to the gates. And what is actually the truth table? So in the logic gates, truth table plays a very important role. So it is a table which gives the relationship between input and output, okay, or it gives the actually the explanation of what is actually the function we have implemented. So what is the Boolean function we have implemented? So those are nothing but the truth table. So coming to the logic gates over here. So first one we have the NOT gate. So the NOT gate is nothing but what? It is the gate which performs the inversion of the input, or we can say it inverts the input. So therefore you can see here, if input is low, then output is going to be high. If input is high, then output is going to be low. And usually we are going to construct NOT gate in not only one gate. Usually we are going to construct NOT gate in the form of IC, that is the integrated circuit or IC chip. So in that, usually you can see here there are 6 NOT gates are there. So therefore this is the 14 pin IC, and the name of this IC is 7404, and it has 6 NOT gates. And you can see here, 1 is the input, 2 is the output, and 3 is the input, 4 is output. Like this, the input and outputs are there, and 7 is used for the ground connection, and 14 is used for the VCC connection, okay. So this is nothing but the NOT gate. And coming to the AND gate, AND gate is nothing but what? AND gate is a gate which its output is high only when two inputs are high. You can can see here only when two inputs are high, the output is high. Or we can say if any one of the input is low, then the output is going to be low. That is also called as the AND gate. And the IC number is 7408. So in the 7408 IC, it is also 14 pin IC. And here again 1, 2 is input and 3 is output. Like this, the things are followed over here. And we have OR gate. So for OR gate, the IC number is 7432 IC. Coming to the truth table, you can see here the output is low, like output is high if any one of the input is high. So you can see here, if any one of the input is high, then the output is going to be high. So that is nothing but the OR gate. And again, it is also 14 pin IC. And here we can see here there are 4 ICs, OR gates are there. 1, 2 is input and 3 is output, and the things are followed like that. The NAND gate is nothing but what? It is AND gate followed by NOT gate. Okay, so that is nothing but the NAND gate, and its IC number is 7400. And again, it is and coming to the truth table or definition of NAND gate. How do I say is, if any one of the input is low, then the output is going to be high. So that is nothing but the NAND gate. Again, you can see here, this is the symbol to represent the NAND gate, and 1, 2 is input and 3 is output. So like this is nothing but the NAND gate. And coming to the NOR gate, this is the truth table. How do I define? If any one of the input is high, then the output is going to be 0. That is nothing but the NOR gate. And you can see here, this is a different configuration. So therefore, when you are doing this experiment, you have to be very careful which is the input and which is the output. So you can see here now 1 is the input and 2, 3 is the input, and this is the circuit symbol. And here 4 is the input, 5, 6 is the 4 is the output, 5, 6 is the input. This is nothing but the 7 and IC number is 7402. And XOR gate is nothing but exclusive OR gate. Okay, and we can say this is also a special gate. And we can say if any one only if any one of the input is high or 0, then only output is going to be 1. This is nothing but the XOR gate. And IC number is 7486, and this is the circuit symbol. Again, 1, 2 is input, 3 is the output. And now we have simplification. So next, this is with respect to the experiment number 2. So in the experiment number 2, we have studied about. In the experiment number 2, we have studied about the basic gates, like how we have constructed, what are the different IC number, and how would be the pin configuration or that. So that we have studied in the second experiment. So that is nothing but the realization of the this thing. Okay. So in the experiment number 3, again we have. In the experiment number 3, you can see here. Just a minute. Okay, so in the experiment number will go like this. So in the experiment number 3, we call which is actually the simplification and realization of SOP and POS function. So what is SOP function? So you know that SOP is nothing but what? It is sum of the products. And what is POS function? Which is nothing but product of the sum. So this is nothing but the SOP and POS. And here in this experiment number 3, we are going to explain how actually the simplification and realization of the SOP and POS function will be there. So coming to the aim of this experiment, it is actually the truth table verification of all the gate. That is, by using SOP and POS function, we are going to verify the truth table, and to simplify and realize a given Boolean expression by using basic and universal gate. Okay, so we'll be using basic gate and also we'll be using the universal gate. As I told you, basic gates means all those things, that is NOT gate, AND gate, OR gate. And coming to the universal gate, the NAND and NOR gate is called as a universal gate. Okay, so by using NAND and NOR gate, we are going to implement the function. And you can see here, coming to the design, it is the realization of given Boolean expression. Okay, so this is with respect to the SOP function and by using the basic gates. Okay. Uh, and this is with respect to the basic gate. Okay, so this is for SOP function, and this is for uh, and this is for the and this is for the pause function. Okay, so you can see here, so this is the expression we are having, y is equals to ab plus a bar b bar. Now I want to implement this function y is equals to ab plus a bar b bar by using basic gate. And you can see here, so this is the SOP function. Why we call it as SOP function? Because it is the sum of product terms. Okay, so AB is one product term and A bar B bar is another product term. Now I am going to sum these two terms. So therefore this is called as SOP term. Okay, so now I have to implement by using this by using basic gate. So you can see here, first one we have AB, A into B. A into B is nothing but what? A into B is nothing but AND function. That is, so I'll be using the AND gate. So you can see here, so this is the AND gate I am using, and A and B are the input. Now again we have A bar and B bar is the another AND function. Okay, so for that what I'll do, what are the inputs to the AND gate here? A bar and B bar. Now I have to invert these input, that is I have to use the NOT gate. So now the NOT gate will be giving me A bar and B bar, and that will be ANDed by using the AND gate. Now I have to perform addition of these two things. So therefore I'll be using OR gate, so thus will be obtaining the output function. So this is nothing but the realization and implementation of the Boolean function by using basic gate, and this is for SOP function. Now this is called as pause function. Why we call it as pause function? Because here it is the sum of product terms, product of sum terms. That means what? A plus B is one sum term and A bar plus B bar is another sum term, and these two will be multiplied by using AND gate. Okay, so you can see here A plus B, plus is nothing but what? It will be performed by using OR gate. So now I'll be using OR gate, and A and B are the two inputs to the OR gate. Now for the another term is nothing but A bar plus B bar. That is nothing but again I have to use again the OR gate, but the input to this is A bar and B bar. How do I obtain A bar and B bar? By using again the NOT gate. NOT gate will be giving me A bar and B bar. So this will be OR, and this will be ANDed or multiplied by using AND gate. So therefore this is the output. So this is with respect to the pause and SOP function by using basic gate. So next I have to implement by using NAND gate, that is the universal gates. Okay, so as I told you, universal gate is nothing but what? Usually it is NAND gate and the NOR gate. Okay, so NAND gate and NOR gate is nothing but the NAND gate and NOR gate is nothing but the NAND gate and NOR gate are nothing but the universal gate. Okay, so how do I do the NAND gate? So you can see here, so this is my expression. What is that my expression? AB plus A bar B bar is one SOP term I'm having, correct? So this is the one SOP term I'm having. So for that, what I have to do? I have to do the double bar. Okay, so so that is nothing but what? The double bar is nothing but what? You know that A plus B whole bar is nothing but what? It is nothing but A bar plus B bar, correct? So therefore A plus B whole bar is nothing but what? It is nothing but A bar into B bar, correct? So therefore here, how do I differentiate it? It is A bar B bar. Next, A bar B bar whole bar is there. Okay, so now I'll be implementing this. So how do I implement this? First one, what I'm having, it is AB whole bar. So AB whole bar is nothing but what? As I told you, you have to use the NAND gate. NAND gate is nothing but what? It performs opposite function of the or inversion of the AND gate. So therefore, if you use AND gate, again you'll be having only AB. But if you use NAND gate, what happens? It is nothing but AB whole bar. So therefore, it is the NAND gate I am using over here. So you can see here, so this is the AB whole bar. Next, A bar B bar whole bar is there. So that how do I perform? So you can see here, so this is the input A I'm having. If I give to NAND gate, then what happens? It will become A bar. Okay, now I'll be having B, and the same input is given to the two input terminal of the NAND gate. So therefore, I'll be having B bar here, because A into A is there and whole bar is there. So again, what it will become? It is A bar, and again here it is B bar. So now if you give to AND gate, it will become A bar into B bar. But if you give to NAND gate, what it will become? It will become A bar B bar whole bar. So again, this will be given to the NAND gate. So if I give to NAND gate, then what happens? It will be ANDed and inverted. So therefore, it is will be inverted. So this is nothing but the thing by using this is the thing which will be obtaining uh, by using your universal gate. Again, the pause function can also be implemented by NAND gate. For that also, I have to do the double bar. Again, A plus B whole bar will become A bar into B bar. Next, A bar plus B bar whole bar will become AB whole bar. Okay. So like that, for this, what I'll do is, for first term is what? A bar into B bar. So for that, what I have to do, A and B input is there. So that will be given to the same two terminal of the NAND gate. So here you'll be obtaining A bar, B bar, and this will be NANDed over here. That is A bar, B bar, whole bar it will become. And again, here you can see here, and what is the other term I'm having? It is AB whole bar. AB whole bar is nothing but what is? It is A and B. The input is given to the NAND gate, so therefore you'll obtain AB whole bar. And again, if you give to this, then the thing here it will become only the NANDed, and if you invert it, then you'll get the actual output. So this is nothing but the NAND gate. Again, for by using NOR gate, again we can implement the thing in this way. Okay, so for all those thing, what we have to do is, so we have to do the double bar. Here for whole term we have to do double bar, but here for the NOR gate we have to do the double bar for each and every term. Okay, each sum term, and for the each product term and each sum term we have to do, and we have to implement in this way. Okay. So next, coming to the procedure, verify all components and patch cards are using the patch card for the connection. So therefore, we have to check whether the patch cards are in proper condition or not. Next, makes the connection as shown in the logic diagram. Then we have to provide the power supply to the digital trainer kit. Then once it on, we have to provide the input data to the circuit using the toggle switches, and we will be verifying the output by looking at the truth table. Okay, coming to the result, truth tables of all the gates are verified, and all the given Boolean expressions are verified using both basic gates as well as universal gate. So this is with respect to the realization of the thing. Next, the fourth experiment we are having is adders and subtractors. So what is adder and subtractor we are having? So you know that adder is nothing but what? Adder is nothing but it is usually adder is nothing but what? It is the combinational circuit. It is the combinational circuit which performs. It is the combinational circuit which performs. Just a minute. So adder is nothing but what? It is the combinational circuit. It is the combinational circuit which performs the addition of the term. So if it is half adder, it performs logical addition of 2 bits, and if it is a full adder, it is going to perform logical addition of 3 bits. So this is nothing but the adder, half adder, and the full adder. So half adder performs logical addition of 2 bits, and the full adder is going to perform logical addition of 3 bits. And coming to the full subtractor, subtractor, again the subtractor is going to subtract the 2 bits. That is nothing but the half subtractor. If it performs the subtraction of 3 bits, then we call it as full subtractor. Okay, so coming to the design, you can see here. So this is the half adder. So this is the actually the truth table of the half adder. Here, these are the two inputs, A and B. Will be having four four sequences, that is 0 0 0 1 1 0 and 1 1. So these are the four states are there. So if 0 0 is added, then you'll get the sum is 0 and carry will also be 0. If you add 0 plus 1, then you'll get 1 and the carry is also 0. And if it is 1 plus 0, then sum will be 1 and carry will be 0. And if you add 1 1, this is the two term. If you add 1 1, then the sum is going to be 0 and carry is going to be 1, because 1 1 is nothing but 1 0. So first term is, or the unit term is sum, and the next term, what we call it as carry term. So therefore carry will be 1. So how do I write this sum term and carry bit? So you can see here we have to look at the sum column. So if I look at the sum column, okay, so if I look at the sum column, where do I see 1 1? Here this is in the second row and the third row. So now I have to look at the second row and the third row. So or if I say, so this is the sum term, so where do I get this column? It is usually I can find in the XOR gate. So in the XOR gate, what you can see, if only when the output is only when one of the input is 1 or 0, during this condition only you'll get the output is 1. So therefore this is the column or the truth table output with respect to the XOR gate. So therefore this is nothing but the A XOR B. And coming to the carry, you can see here, so this column will be with respect to the AND gate. Okay, so this is with respect to the AND gate, that is A into B. So how do I represent this? So how do I get the sum of the two bits? That is by using the XOR gate. If I give the two inputs AB to the XOR gate, then I can obtain the sum. If I want carry, then what I have to do? I have to use the AND gate. If I use the AND gate, then what happens? It multiplies and it will give you the carry. So therefore this is nothing but the half adder circuit by using the logic gates. And coming to the half adder using NAND gate, that is using a universal gate. Again, what I'll do, so first of all I'll be NANDing these two terms, and again I am going to use two other NAND gate. So therefore, and this will be given to again to the another NAND gate. So this will give you the sum and this will give you the carry. So this is with respect to the universal gate. And coming to the full adder, again here three terms are there, 0 0 0 0, that is A, B and C are there. So this is with respect to sum and this is with respect to carry. So how do I obtain the Boolean expression over here? So how do I obtain? So you can see here, you have to look at the sum term, and wherever the 1 is there, so that term you have to write. You can see here, this is with respect to the second row. So how do I write this? 0 0 means what? It is A bar, B bar and C in. So I'll write A bar, B bar, C in, plus again here it is what? It is A bar, B, C in bar. Like that we have to write, and we simplify this, you'll obtain A XOR B XOR C. So therefore XORing of 3 bits will give you the sum bit. And how do I obtain the carry bit, which is nothing but AB plus BC plus AB plus BC plus AB plus BC plus C into A. So this will give you the carry term. So this can be implemented by using this. Okay. So you can see here, so this is the XOR gate I'm having. So by using this XOR gate, combination of this XOR gate will give you sum, and AB plus BC plus CA. So everything will give you the carry term. And we can also implement by using the special gate also. It's coming to the half subtractor. So it is nothing but what? Again, the difference can be obtained by using XOR gate, and the sum can be obtained by using A bar into B. So that will give you the borrow. Okay, difference can be obtained by A XOR B, and borrow can be obtained by A bar B, and that can also be implemented by using the NAND gate. So this is the truth table of the half subtractor. And coming to the full subtractor. You can see here, so this is the truth table of full subtractor. You can see here the sum again, this is the difference and this is the borrow. By looking at the truth table, we can implement these two functions, that is the difference and the borrow, and these can be implemented same way with respect to that. Okay, so this is by using basic gates, and this can be represented by using the logic gate. Sorry, that is by using universal gate. Procedure again, verify whether all the components and patch cards are in good condition. That is, we have to verify the ICs also and make the connection as shown in the logic circuit diagram, and the provide power supply to the digital chain, okay, and provide the input data by using the toggle switches, and we have to verify truth table sequence, and we have to observe the output. And coming to the result, truth table of half adder, full adder, half subtractor and full subtractor are verified. And coming to the RC coupled amplifier. So coming to the RC coupled amplifier, so this is the last experiment in the in BJT. Okay, so aim of by using BJT and also to determine its bandwidth, input and output impedances. So what is actually the RC coupled amplifier? So we know that amplifier is nothing but what? It amplifies the signal, or it strengthens the weaker signal, or it increases the amplitude of the weaker signal. So that is actually the amplifier. So these amplifier can also be constructed by using BJT and also by using the resistor and capacitor combination. Or this is only I'm explaining you about single stage RC coupled amplifier. If you have the two stage RC coupled amplifier, then both stages can be coupled by using only the capacitors. Okay, so therefore these are nothing but the RC coupled. Why? Because in the circuit you will find only the BJT, resistor and capacitor. Apart from this, you won't find any of the other semiconductor devices. So therefore this is called as RC coupled amplifier, and will be determining its bandwidth. So bandwidth is nothing but what? It is the range of frequency. Okay, so in the range of frequency, where it is going to amplify the signal, so that is nothing but the bandwidth. And coming to the input and output impedance, so it is the impedance which is looking at the input side, which is nothing but the input impedance. If the impedance is looking at the output side, then we call it as the output impedance. So these things will be determined in the RC coupled amplifier. Next, coming to the BJT, we know that BJT is a current control device. BJT is nothing but what? It is bipolar junction transistor, and it is a current control device. Why we call it as current control device? Because if you vary a base current of the transistor, then you can actually turn on or turn off the transistor. Again, transistor is also going to be act as a switch, or it can also be used as a amplifier. So therefore, if you vary the base current, then you can actually on and off the transistor. So therefore, it is called as current controlled device. Mainly, it is depend on the base current. Then application of this RC coupled amplifier, it is usually used to design switches. That is BJT is usually used for the designing of switches and variety of amplifier. And usually this RC coupled amplifier is used in RF communication and optical communication as an amplifier. Okay, and we know that there are three stages in the transistor, that is in the output characteristics of transistor. One thing, we have active region, but then we have saturation, then we have a cutoff region. So these are the three regions. So amplifier action can be obtained only in the active region. Okay, that is base emitter junction should be forward biased, and emitter collector junction should be reverse biased. During that condition only, it is going to act as amplifier. The most suitable configuration is only the common emitter mode. And what is biasing? If we connect the external DC power supply to the transistor, then we call it as a biasing. For transistor amplifier, Q point is that is the operating point or quiescent point will be selected at the middle of the DC load line. And capacitors, two capacitors are used. That is we call it as the coupling capacitor. Why? Because it separates the AC signal from the DC biasing voltage. So therefore, this is nothing but the coupling capacitors. And we are going to use the emitter resistance, which stabilizes the biasing circuit. and it is the common source class A small signal amplifier, which is used as a voltage amplifier also, and in the audio frequency range. In RC coupled amplifier, coupling from one stage to the other stage is achieved by R and C elements, and this amplifier provides better frequency response characteristics. Okay, and in the single stage amplifier, we will be having 180-degree phase shift, and in the two stage, we'll be having 360-degree phase shift of input and output signal. So this is the circuit diagram. We are going to choose the SL100 transistor, and the connection will be goes like this. That is the collector will be connected to resistor RC, and again it is connected to R1, R2. This is something acts like a resistance or potential divider circuit, and the base is connected to this junction, and then from this junction we are going to connect to C1, that is the C1 coupling capacitor, and this will be connected to the function generator or to the input. Again, these things will be grounded, and the emitter is connected to the emitter resistor RE, and again across this we are going to connect again one of the another capacitor C, and that also be other end will be grounded. And from this junction, that is from the collector junction, it is connected to capacitor C2, and this is connected to load resistor, and this junction is also be grounded. So usually the ranges will be selected in this range, or we are going to design the circuit in this range. That is VCC is selected as 10 volt, and R1 is selected as 22 kilo ohm, and R2 is selected as 4.7 kilo ohm, and RC is selected as 1 kilo ohm, RE is selected as 220 ohm, RL is 10 kilo ohm, and C is 10 microfarad. C1, C2 is usually 0.47 microfarad. It's coming to the design procedure. You can see here. So this is actually the equivalent module of this circuit, model of this circuit. You can see here. So this is the transistor we are having. So for analyzing the circuit, what we will do is, so the DC components are open circuited. Okay, usually the capacitors what we are having, removing those capacitors, we will be retaining only the resistors combination. Okay, that is for the analyzing purpose. The all DC components, that is capacitors, are open circuited. So therefore we are going to select the VCC, that is the collector voltage will be taken as 10 volts. So usually the voltage between collector and emitter will be half of that, so therefore it will be 5 volts. And therefore IC is 4 milliamps, beta is nothing but 100, IB is nothing but what? It is nothing but IC by beta, we know that, which is nothing but 0.04 milliamps. That is, this can be calculated by selecting these ranges. And we know that emitter current is nothing but sum of these two current, that is base current and collector current, which is nothing but 4.04 milliamps. And to find RE, we are selecting V as VCC by 10, which is nothing but 1 volt. And RE is nothing but again VE by IE, we know that. So 1 by 4.04, you will get 220 ohm. And to find RC, we have to apply the KVL to the output circuit. So you can see here, so this is the output circuit we are having. So which is nothing but what? It is VCC minus ICRC minus VCE minus VE. Okay, so this is the output circuit we are having. So we have all these terms. So therefore, I could calculate RC from this equation. I know VCC, VCE, VE, and also I know IC. So therefore, RC can be calculated. It is usually 1 kilo ohm. And to find R2, correct? So we have again R2. So to find R2, the current entering into the base is IB, correct? So the base current is IB. So let current through R1 is also 10 times IB. Okay, so this we are going to assume. Again, apply KCL at the node B. So this is the node B I am having. So if I apply the current, usually what happen? KCL is nothing but what? It is entering current will be equal to the outgoing current. So how do I write this? So therefore, I1 is nothing but I2 plus IB. So therefore, I2 is nothing but what? 9 times of IB. And voltage across R2, it is VE plus VB. You can see here. So it is VE plus VB. It is 1.7 volt. And current through R2. So this current through R2 can be usually 9 times of IB. So therefore, it is 0.36 milliamps. And to find R1, it is voltage across R1. So this is nothing but what? So this is usually VCC minus VB. Okay. So it is 8.3 volts and current through R1 is 10 times of IB. So therefore it is 0.4 milliamps. R1 is nothing but V1 by I1. It is usually 22 kilo. So therefore design for C1, C2 and CE, coupling capacitor C1 is equals to C2 is selected in such a way that reactance of XC1 is less than Thevenin's RTH voltage at low frequency 50 Hertz. Okay. And RTH is nothing but 3.873 and C1 is greater than 0.41. So therefore we are going to select 0.47 microfarad. Bypass capacitor C is selected in such a way that reactance XCE is less than RE. Okay, and CE is usually greater than 7.23 microfarad. So this is with respect to the designing part. Coming to the procedure, make the connections as shown in the circuit diagram. Adjust the peak to peak voltage of input signal 20 milli VPP using 40 dB attenuation in the signal generator. That means we are going to give input from the signal generator and input will be selected in this way, and we have to vary input signal frequency from 10 Hertz to 2 megahertz for each input frequency. That means here the varying thing is frequency. So we have to vary the frequency in the signal generator, and we will be measuring peak to peak voltage by looking at the CRO, and we are going to tabulate the reading, and we have to calculate the dB, that is the voltage gain, using the formula 20 log V out by Vn. So this is the gain formula, voltage gain formula, and we will be plotting the frequency response in the semi-log graph sheet. So here we are going to use the semi-log graph sheet, not a ordinary graph sheet. And we have to mark minus 3 dB point from the maximum dB. That will give you lower and higher cutoff frequency, and thus we can determine the bandwidth. So to measure output impedance Z out, so the connections will be something like this. So we'll be having input, that is the signal generator, RC coupled amplifier, and the DRB box. Okay. So we have to make the connection in this way, and we have to initially keep the DRB in a maximum position, that is to the maximum resistance value. And keeping VM 20 milli VPP, that is peak to peak voltage, we have to set the signal generator frequency to 100 kilohertz, at which output voltage is maximum. So this at this particular frequency we will be measuring the output voltage. Now we have to note down the output voltage, which is V1, and we have to decrease the value of DRB until output voltage reduces to V1 by 2. Okay. So at that stage also we have to note down the impedance, that is the Z out, that is nothing but the R out. So this is the procedure to calculate the output impedance Z out. Tabular column. So keeping V in 20 millivolts, so we will do this. So you can see here we are going to vary the frequency in the signal generator for varying, like at every instant of varying the frequency, we'll be measuring the output voltage. Will be measuring the output voltage, and by using this we'll be measuring voltage gain and the voltage gain in decibel. Okay, so the graph will be something like this. So this is nothing but the frequency response plot. What is actually the frequency response plot? It is the graph of voltage gain versus voltage gain versus frequency. So this graph is nothing but the frequency response. So from this frequency response, you can notice that, so this is the F1 is the lower cutoff frequency, that is this is the maximum frequency, minus 3 dB from this maximum frequency. This is nothing but the lower cutoff frequency, and this is the higher cutoff frequency. So what do actually we can observe from this graph is the bandwidth or the gain is going to be constant in this mid frequency range. Okay, so in this frequency range you can see the gain is almost constant. Okay, so this is nothing but the bandwidth, and apart from this lower cutoff frequency, higher cutoff frequency, the gain is going to be reduced. So this we can observe. So this you will observe in the practical session also. Okay, thanks for watching the video. Thank you, students. So the result can also be done like this. Okay, thank you.